Assalamu alaikum. Hello, student. As I promised, I will be explaining Unit 2 or Chapter 2 in this video. The first slide shows a refrigerator with its door open, placed in well-sealed and insulated room. What do you think will happen to the room temperature? In this case, the electrical energy supplied to the fridge runs the compressor, which release heat into the air inside room. As we can see here, the system is assumed to be adiabatic, which means the room is well sealed and well insulated, so no heat transfer occurs into or out of the system. As a result of the conversion of electrical energy consumed by the refrigerator into heat, the room temperature will rise. Now, can you tell me what will happen to the other room with the fan running? Energy can exist in many forms, such as thermal, mechanical, kinetic, potential, electrical, magnetic, chemical, and nuclear. The total energy of a system is the sum of all these different type of energy, and the symbol will be E. Let's talk about the difference between micro and micro. I don't know, maybe the difference it's difficult to pronounce, macro and micro. So macro with A generally refers to something that is large scale or big. On the other hand, micro refers to something that is small scale or tiny. Macroscopic energy deals with energy of the whole system, like car moving in this case, or lifting something. Microscopic energy deals with tiny particles inside the system, like how fast the molecules inside the car engine are moving, or inside piston or system. And an example of macroscopic forms of energy is when car moving or changing its elevation, we can calculate the kinetic energy from its motion, or the potential energy from its position. For the car as the whole system, we deal like with whole system. On the other hand, an example of micro forms of energy is internal energy, and this is very important. We will discuss next slide. Like internal energy inside the car engine. Here we can treat the engine as whole system, and we look at the energy of the molecules and particles inside it, which is called internal energy, and the symbol is U. This internal energy includes both of kinetic energy, potential energy, and particles that are moving and interacting inside the engine. Now we can see the formulas of the kinetic energy, and most of you, I think, remember the equation, which is the mass multiplied for the kinetic energy, mass or m multiplied by half velocity square, and the unit will be kilojoule. But for the kinetic energy per unit mass, we divide by the mass, and the mass will be gone, and so we left with velocity square over 2, or we can say half v square. We can say, sorry, this is moving, so let me write it again. So half v square. and you can see the difference in the unit kilojoule per kilogram, because we divide by by unit mass, and the mass with the mass will be gone. We left with the unit. Also, same thing for the potential energy. I think you still remember, it's the mass multiplied by the gravity, and z, which is the displacement, or the height, or whatever the movement happened to the object. And again, for the potential energy per unit mass, we divide by the mass, and we left with this, and the equation will be same as the kinetic energy per unit mass. Now, as we explained before, the total energy of the system will be the internal energy, which is capital U, plus the kinetic energy plus the potential energy, which means it's the sum of all these different forms of energy. And the details of each terms we have already explained here, for the kinetic energy, for the potential energy. For the energy of system per unit mass, it will be the same concept, which we will divide by each term per unit mass, and we will left with this equation, which is small symbols, and the equation will be different from the unit will be different from the other unit. Now, if you want to make this easier for you, you can say the whole thing divided by unit mass. It will be this equation, and we know which is E is the total of all the forms of energy available. In this slide, we will talk about the internal energy. Internal energy is the sum of all energy on the microscopic level, and it's composed of four, which is sensible energy, latent energy, chemical energy, and nuclear energy. We can see here for the sensible and latent energy is related with the movement of molecules, like kinetic energy. But for the chemical energy is related to the atom bonds, and for the nuclear energy is the tremendous amount of energy associated with the strong bond with the nuclear of the atom itself. And here's examples of the sensible and latent energy, like this one, and this is for the nuclear energy. Here, this means and sensible and latent energy, it's thermal, it's heat, like it's related with temperature. But all of these four types, it's internal energy. For this slide, it's explained let me just hide this one. For this slide, it's focused on the heat transfer and work, which are the only two ways energy can be transferred across the boundary of a system. And you can there are two types, which is first let's talk about the two types of energy: the static forms of energy and dynamic forms of energy. Static forms of energy refers to energy that is stored with the system, This include forms of energy such as internal energy, potential energy, which do not cross the boundary of the system during a process. Dynamic forms of energy or energy interactions are those that can cross the system boundary, like heat and work. And in this figure we can see just the difference, the idea of this figure, just to show the difference between the micro and macroscopic energy. And we can see the here is the macro kinetic energy is organized from organized form of energy and is much more useful than the disorganized of microscopic kinetic energy of molecules. In this slide, I will talk about the flow, flow fluid, or maybe we call it flow work. If you remember, by the way, this slide is not from the book. I brought it from the internet, so it's not explained in the book. Maybe it's explained, but it's not. It was not clear. One of the, if you remember, one of the students asked me, "What is BV?" So one of the internal energy when we solve, the exercise, it was BB, and or maybe it was B rho, if you still remember. And one of the students asked me from where we bring this, or from where we got this. So all of you know what's the pressure equation will be force over area. And we can before that, let's look at the definition of flow work or flow energy. It's the work or energy required to push the mass into or out of the control volume. This work is necessary for maintaining a continuous flow through a control volume. So if you still remember this equation, we can make it like this equation, which is the force. So now the work, we can say the flow work is, if you remember, work is equal force multiplied by distance or displacement. So L here will represent the distance or replacement. So what's F is equal? F is equal pressure multiplied by the area. So again, F is equal pressure multiplied by the area multiplied by the distance or the length or whatever. But if we see the area multiplying by the distance or the displacement, we can replace this by the volume. So the workflow or the flow work, sorry, it will be B multiplied by or the pressure multiplied by the volume. And if we multiply by the specific volume or by the mass, it will be B small, it will be the B by the small v, and we can say B over rho. So this is the idea of this slide. Now we can see here, this is the equation, if you still remember this equation. So we call this equation is mechanical energy, and mechanical energy containing of multiple terms. One of the terms is called the flow work, and this is the kinetic energy, and this is the potential energy. And these things, it's like as the previous slide, when you want to find the rate, I have explained this before. When you add dot, it's called the rate, so it's respect to the time. So it will be the rate of the mechanical energy of a flowing fluid which is the mass flow rate. So again, here mass will be with dot, and E is the mechanical energy, which is this form. So this is the equation for the rate of mechanical energy of flowing fluid. And this is will be the difference, or the we can call it the change of the mechanical energy, and you find the final minus the initial, final minus initial, final minus initial, and the rate of the mechanical energy change of a fluid during incompressible flow will be the change of the mechanical energy, which is the whole thing multiplied by the mass flow rate. I will be back just 1 minute. Now let's continue. You can see so this slide is explaining the equations for this for this slide, but the main thing in this slide is to show you for the mechanical energy equation, we can delete some terms like these three terms. So in this example, we can see there is only change in the potential energy, and the pressure here in 1 and pressure in 4 will be the atmospheric pressure, but there is no kinetic energy, so the system is not moving with the velocity, so the only change is the potential energy. So these can cancel, and we left with the mass flow rate multiplied by the gravity and the change of the position. And in this figure we can see the mechanical energy, which is the only thing, the velocity, there is no kinetic energy and there is no potential energy. So the only thing you can see is the pressure will be different in 2 and 3. So we can find the change of the flow work. For the next slide, is talking about the energy transferred by heat. So heat is the form of energy that is transferred between two systems or a system and its surrounding because of temperature difference. As you can see in this figure, the room temperature is 25. So if you have one can with 5 degrees Celsius and the other can with 15 degrees Celsius, and the third can will be the same temperature with room temperature, there is no heat transfer, and they will be adding for heat transfer until it becomes in equilibrium. Also, the heat transfer the transfer of heat into a system is frequently referred to as a heat addition. So when heat is going in, it will be heat addition, and when the transfer of heat out of the system as heat rejection. For this slide, it shows the idea or how heat transfer happened. It's like they give an example of baked potato. So of course it's hot inside, but this is considered as energy. But when it's transferring from the inside to the surrounding, of course it will pass through the boundary. So energy is recognized as heat transfer only as it's across the boundary, the system boundary. And they shows the difference between uh, the heat transfer. The small letter will be the heat transfer per unit mass, and Q is the heat transfer itself, and Q dot is the rate of heat transfer. I would explain first something they have not explained. So because you thought this is the only equation to find the Q, but you know the first law of thermodynamics state that Q minus work, so Q is the heat transfer, equal delta E. So this is the main equation, but and usually Q is given, or you can use this to find the Q. So if you have it given and you want to find the heat transfer per unit mass, you can use this equation. And for the heat transfer, if it's the amount of heat transfer when heat transfer is rate is constant, you can use this equation. But if it's the amount of heat transfer when heat transfer rate change with time, you can do the integration to find a Q. So last thing in this slide, let's talk about the adiabatic system, and we have talked about this when a system is well insulated. It's a adiabatic system, so there is no heat transfer. And this slide it's provide a historical perspective on how heat was understood in the early 19th century. It was believed that heat was an invisible fluid called caloric, which flowed from a warmer body to a cooler one. But this theory was later replaced by the kinetic theory, which reflected that heat is actual energy associated with the random motion of atoms and molecules. Now we can, now we know that heat transfers in the three main ways, which is conduction, where energy moves through the direct contact between particles, and there is a convection, which happens when heat is carried by a fluid like air or water as it moves over surface. And the last one is radiation, where energy is transferred through electromagnetic waves such as sunlight. In this slide, we will talk about the energy transfer by work. Work, the energy transfer associated with a force acting through distance, like raising position, rotating shaft, and an electrical crossing the system boundary, are all associated with work interaction. Formal sign convection, this is very important, but maybe it's confusing here. So they said heat transfer to a system is positive, and so they said heat transfer to a system and work done by a system are positive. So this is work done by a system, so this is positive. Okay. And heat transfer, they should say out from a system, heat transfer out from a system and work done by a system are negative. So this is, sorry, So this is negative, and this is negative. Again, heat transfer to a system and work done by a system are positive. Heat transfer from a system and work done by us done on the system are negative. So sorry, I think I confused you. Sorry. 1 minute. Let me repeat this. Again, heat transfer to a system. So this is to the system is positive. Is positive. Heat transfer to a system and work done by a system. So the system did the work and the work went out. So this positive. Okay. Heat transfer from a system, so it went out from the system, it will be negative. Heat transfer from a system and work done on the system are negative. So you do the work on the system, so it will be negative. I hope this is clear now. And work done per unit mass, you multiply by you divide by mass, so it will become small. And this will be the equation. This is confusing a little bit, but let me try to explain it. So the idea to just to show these two equation. So if you have a volume or specific volume or whatever, and you have two states, and we know these the path. So for state 1, and you move from state 1 to state 2, and whatever you take the path, any path, at the end we will find delta V, the change of the volume. So the final one, negative or minus the initial one, will be 5 minus 3, which is minus 2, which will be 3. So we don't care about which path you took. This is for volume. So the idea, the properties, it will not help us, or it will not affect. But for the work, it's important if you have work in state 1 and work in state 2, and you can when you take this path, the work will be different when you take the other path. So we cannot say delta or the change of work. We should say work from state 1 to 2, and we consider the state 1 and all the properties as state 1, and we consider all the properties as state 2, and we find the work. And you can see with the examples in next chapters, you can understand this. So for this slide, it's talk about the work for the electrical work. Work is one form of energy transfer, and one type of work is electrical work, which is occur when an electrical charge moves through potential difference, and it can be expressed as this one, which is the work of electrical work equal the potential time n, where V is the voltage, like V voltage move through a certain amount of charge. So the n is the certain amount of charge performing on the system that was performed on a system. And if you want to find the electrical power, you multiply the voltage by the current, and when potential difference and current change within time. So if there is time, you have to find the integration of the voltage multiplied by the current and delta t. So the last equation, when potential difference and current remain constant, we can use this equation. And of course, this is kilojoule. This will be watt. And this is kilojoule because there is no time with it. Now for this, the mechanical forms of work, there are two requirements for work, interaction between system and its surrounding to exist. There must be a force acting at the boundary, and the boundary must move. So I think all of you remember the work is if the force multiplied by distance, and when we want to find the force, when the force is not constant, we can find the integration of the force multiplied by the distance, change the distance, and the work is done is proportional to the force applied and the distance traveled. So when when force is higher, we need more work. When we have long distance, we need more. I mean, the work is more required. For the shaft work, we all know the torque, which is a force acting through a moment arm, R, generate a torque. So I think you still remember this equation. Torque will multiply by force multiplied by R, which is circular, and we can change the form of this equation. And for the force through a distance, we can use this equation, because it's the distance will be the number of revolutions for the shaft. So we consider the radius and how many time it's rotating or revolution happened. So we put these two equations together, and we know the work will be force multiplied by distance, and force we know when we change the form of the formula, it become like this. For S, it's the revolution, number of revolution will be this. So R cancel with R, we left with this equation. So this is the power transmission through the shaft, is the shaft work done by per unit time. So this is the equation you will see. For this slide, it's talk about the spring work. Same thing, when the length of the spring is changing by differential amount dx under the influence of a force, if the work done is force multiplied by the different amount of dx, which is the change of the displacement. Yeah, the change of displacement. For linear elastic spring, the displacement x is proportional to the force applied. So we know x is the displacement, k is constant, spring constant here. So work, when we want to find the work, we put these equations together, and we have the final equation, which is half of the spring constant multiplied by the change of distance, displacement, which is the final minus the initial. I will stop at this slide. I will continue in a couple of hours, and I will finish the whole chapter tonight. Thank you.